Hello, Professor Wolkowitz. In this quick video, I'm going to be going over my final project where I discuss the wind turbine rotor speed and yaw control. Quick system overview. Several inputs can be controlled when looking at the motion of a wind turbine, but for simplicity, we're going to be looking at rotor speed and yaw angle. The main objective is to maximize wind energy based on these two parameters. And by doing that, we want to implement a target rotor speed that will maximize the amount of wind energy without overpowering the turbine, so 400 RPM was selected. And we also want to align the wind turbine with the wind direction to maximize wind energy, and that was assumed at a constant 60-degree angle. Software integration, first of all, target system performance. The rotor speed, we want to have a rotor speed within plus or minus 20% of 400 RPM. And for the yaw, we want the wind turbine to be aligned within plus or minus 10% of the 60-degree wind direction. Controller implementation, a PID was selected based on its common application in wind turbine systems, but LQR was considered but not used because no weighting is used between rotor and yaw. PID challenges and implementation. Basically, it started with a step input of either a desired rotor speed and yaw, followed by the PID, followed by other parameters, and we'll get into these other auto-tuning and iterative solving methods with the PID later. System modeling for the rotor speed. As far as the system was derived, a predetermined transfer function from the textbook was implemented, which can be seen here, and it was converted to a state space model to better demonstrate the states of that system. Techniques used, system parameters were input into a MATLAB script. These parameters were input also from the textbook, and of note, simplification was performed to appropriately create the matrix for the denominator, just for coefficients of varying degrees of s in the transfer function. And we also used the transfer function to state space feature on MATLAB to create the state space model for the rotor speed, which can be seen here. And of note, the three states of this system are pitch angle, generator speed, and rotor speed. For the yaw angle, a very similar approach was used. Of note, this was based on a aircraft system, so it was simplified accordingly to better suit a wind turbine. And as can be seen here, we have four states, but the yaw angle is the only state of interest. Continuous and discrete mass for the system. Rotor speed auto-tune was used due to concerns of stability with the transfer function. A PID controller was implemented. For the yaw, iterative solving was used. We wanted to change the gains accordingly to achieve the yaw that we wanted. Potential concerns with nonlinearity. For the rotor speed, the model became more linearized with the auto-tune. It was more robust, and robustness helped minimize overshoot and stabilize the rotor speed. For the yaw angle, iteratively solving causes a lot of uncertainty, and effective overshoot and stability are more pronounced and difficult to account for. And thus, it can still be used and is accurate enough if research and testing is performed to determine the gains appropriately. System mockup for the rotor speed. It's a simple feedback control loop system. For the PID, these were the gains created by the auto-tuning feature, and this disturbance block, which is modeled as the wind, parameters can be seen here. Similarly, for the yaw angle, these were the iterative gains used and the parameters from the pulse block. It's important to note that a period of 2 seconds were applied to both rotor speed and yaw angle models, and also because yaw and rotor speed are affected differently, the disturbances were not as pronounced as one compared to the other. System results and development. Simulink model mockup for the wind turbine speed can be seen here. It's within plus or minus 20% of the rotor speed, erring on the side of minus 20%, but variations do not matter as much because 400 RPM was safely selected such that the generator didn't overheat. Similarly, for the yaw angle, as mentioned, some overshoot can be seen, but once it was tuned, it stabilizes much better at about 60 degrees. System concerns, it's obviously not as entirely accurate. Rotor speed, only safe wind speeds were concerned. Only one rotor speed was tested, so we could test at multiple different rotor speeds. As far as the yaw is concerned, wind speeds are not constantly blowing in one direction because wind directions are always changing. And by increasing the effect from the disturbances, we can better see how the system is better equipped to handle these disturbances. Of note, general system results, I'm not going to go through all of these, but in general, efficiency is not incredibly ideal, but as mentioned, by testing at these different rotor speeds, we can test to see how much power is generated and how efficiency can change with time.